Right. Hello. Good evening, everyone. Good evening. We'll start discussing the gases, the tutorial related to gases and the chemical calculation. What do you want to discuss first? The gases tutorial or the chemical calculations, meaning titrations? What do you like to discuss first? What do you think? Huh? Right, gases. Okay. So we will work on gases then, right? First to say is gases, right? Titrations. Now you are a little late, right? First to say is gases. So let's look at that. Right. Okay. So starting from question number, what is the question number? Question number 51, I think. That was the last question we, 50 we discussed. Question number 51 to discuss. Right. Let us work that out. Question number 51. 51 is the question, right? Derive the equation PV is equal to nRT using three main gas laws. Calculate the value of R using SI units. How do you modify the equation to explain the behavior of the non-ideal gases? Explain your answer. Let us look at that. We said that according to the Boyle's law, volume is inversely proportional to pressure. According to the Charles law, volume is proportional to the absolute temperature. And according to the Avogadro's theory, volume is proportional to the number of moles. So if you combine these three things, volume is proportional to 1 over P times temperature times the number of moles, right? And then get rid of the proportionality constant. V is equal R Tn over P. And we understand that this is PV is equal to nRT. So that's your equation, right? And then they ask you to calculate R. R you calculate using PV divided by NT. PV divided by NT, right? You use ideal gas conditions. Pressure is 1.013 10 to the power 5 pascals. Pascals Newton per square meter. Volume is, remember 22.414, 22.414, 10 to the power minus 3 cubic meters. N is 1 mole of this material. Temperature is 273, 3.16, I think, but we'll say 273. What would be the value that you get? 1.013 10 to the power 5 multiplied by 22.414 10 to the power minus 3, I think. This is equal to, right, multiplied by 22.414 10 to the power minus 3. That is divided by 273. 8.3169 is what I get. 8.314 is the actual value. Based on these values, you will get 316 joules per moles per Kelvin. But the real value is 8.314 is the real value that you usually get. Is it clear? Right. And then it says, how do you modify the equation to explain the behavior of the non-ideal gases? This is the Van der Waals equation that we use. P plus, what is the equation? N squared A divided by V squared. Then what is the next one? V minus NB is equal to what? Is equal to nRT. That is that equation that you get. So what is this? A is the Van der Waals equation or Van der Waals constant. Van der Waals constant for intermolecular forces, IMF, right? B is the Van der Waals constant for internal volume. You remember that? Constant for volume, internal volume, internal volume. And because of the intermolecular forces, the pressure drop is N squared A divided by V squared. If the intermolecular forces are not there, Actual pressure is pressure observed plus whatever the pressure dropped. So that is how you get this correction. V minus NB, total volume is V, internal volume of 1 mole is simple B, total volume is NB. So volume available for the particles to move about is V minus NB is equal to nRT. It is in the note. But then I reminded you, right? So rather than I'm not going to write that, but that is how you get that. So you get these two corrections into PV and RT, where you get the van der Waals equation with the proper corrections. I hope you got the idea. That's all. Explain your answer. That's all. Then we will go to the next one. Calculate the density of the gas, this temperature, this pressure, molar mass is this much. PV is equal to nRT. PV is equal to simple M divided by capital MRT. P capital M is equal to DRT. So density is equal to, what is that? PM divided by RT. Right. Let's substitute those values. Pressure. Pressure they have given 30.4, 10 to the power 5 pascals. So Newton per square meter. Molecular mass is 16 grams per moles. So let's convert it to kilograms. Take 16, 10 to the power minus 3 kilograms per moles. Universal gas constant. What is the universal gas constant? That is 8.314, 8.314 joules per moles per Kelvin. What is the temperature? Temperature is 29.5. So that is 29.5 plus 273 is equal to what is that? To 29.5 plus 273 is equal to 605 divided by 2. Okay, 605 divided by 2. What is the temperature? Kelvin. Huh? So let us simplify some of these things. Kelvin per Kelvin cancels out. Per moles cancels out. Joule means Newton meters. Newton meters, Newton and Newton cancels out, right? And you get kilograms per cubic meter. That is, I think that is what I get. 10 to the power minus 3. This is 10 to the power 2, right? And that's all. I think, shall we simplify that? And then let's say we can get that 30.4 multiplied by 16 multiplied by 2 divided by, what is the number? Divided by 8.314. That is divided by 605. You get 19.34. 19.1934 kilo. Is that what you get? 0.1934. Right? I think that is the answer. No, like 19.34 kilogram. Yeah, I didn't take the 100. No? Yeah, I didn't take the 100. Sorry. So it should be 19. Huh? 10 to the power 2, I didn't take that. So 19.34 is the answer. Is it clear? Yeah. Yeah, 10 to the power 2, I haven't considered. Question number 51 is that. Huh? That answer is okay. 605 is 273 plus 29.5. Whatever the answer is equal to 605 divided by 2. Right? Question number 52. If you don't want to discuss that, tell me, right? If you got those answers and you're okay, that is, yeah. Okay. Question number 52. Right, let's read the question. 31.2 grams of NO and 20 grams of oxygen is confined into this flask at 27 degrees Celsius. Calculate the difference between the initial and the final pressures after the reaction has taken place. Right. Let's see whether what is the reaction. First of all, you have NO, number of moles of NO is equal to 31.2. What is the molecular mass? 14 plus 16, right? 14 plus 16 is 30. 30 grams per moles. So what is the number of moles that you get? 31.2 divided by 30 is equal to, uh, what is the answer? 26 divided by 25. I get this number. I don't know how to convert this into this. What is this? 31.2 divided by 30 is your answer. This one is 26 divided by 25. When you divide this, right? Whatever the number that you get, right? Okay. And then what is the next one? Next one is number of moles of oxygen, 20 grams. Huh? Number of moles of oxygen, 20 grams. So 20 divided by 32 moles. 20 divided by 32 moles. Mm. So this is the number of moles, right? 20 divided by 32, can you tell me? Just a minute. I'll get a proper calculator. This is like a kind of a little bit of a problem. Yeah, okay, right. I'm back, right? So what is this answer? 26 divided by 25. It will give you 1.04. 1.04 moles. And the next one is 20 divided by 32. It will give you 0.625. Right. Let us now apply the total pressure. Let's calculate the total pressure. Yeah, thank you. Thank you. You have sent me the answers also. Thank you very much. Let us look at the pressure. Pressure is equal, PV is equal to nRT. nRT divided by volume. What is the number of moles? 1.04 plus 0.625. 625 moles. Right? I'm going to bring that equation over here. So that is easy, right? Multiplied by R is equal to 8.314 joules per moles per Kelvin. Joules per moles per Kelvin. And what is the temperature? Temperature looks like, what is the temperature? 300 Kelvin. 300 Kelvin, and the volume that they have taken is 2 10 to the power minus 2 cubic meters, right? So finally, this gives you the pressure in pascals. What would be the answer? 1.04 plus 0.625, right? Multiplied by 8.314 multiplied by 300 divided by 2 10 to the power minus 2 is equal to 2.07 10 to the power 1, 2, 3, 4, 5. 2.076 10 to the power 5 pascals. Did you understand that? 2.05 10 to the power 5 pascals. Everybody got it? Ah, well done. Right. Okay. Good. Right. Right. Is it clear? Hmm. Right, okay. So 2.076 10 to the power 5, right? Okay. Now what we are going to do is this, the next one. Let us say this is going to react. Like, let's say it's going to react there, right? What is the reaction? This one has NO plus O2, NO2. NO gas plus O2 giving you NO2. This is 2NO2. Now we need to look at how, like the gas, get the rice chart and then see how the reaction take place. This is the reaction. What is the initial number of moles? Initial number of moles, 1.04, 0.625. 1.04 and this one is 0.625. There's nothing here. I hope you got the idea, right? Yeah. So if you want all that oxygen to react, I'm going to look at the limiting reagent. If you want all that oxygen to react, how many moles of NO do you need? If it is 1 here, you need 2 moles. 0.625 multiplied by 2 gives you 1.25. Now, if it is 0.625 to react, you have to have 1.25, but you don't have 1.25. So that means NO is the limiting reagent. Did you understand that? NO is the limiting reagent. So change, I am going to say that 1.04 act as the limiting reagent, right? And this one 0.52, 1.04 divided by 2. This gives you 0.52. So 0.52 moles has reacted. And this is 2 is to 2, then it will give you 1.04 moles. Right? And that will give you 0 here. This will give you 0.625 minus 0.52 is equal to 0.105. 0.105 moles. That is the remaining amount. And other than that, you have 1.04 of NO2 gas that is formed. Everybody understood that? Is it clear? Right? Is it clear? Did you understand that? Limiting reagent, it comes from chemical calculations. If you have 1.02 to react, 2 to 1, right? 2 to 1. So if there's 1.04, you need half the value for oxygen to react. 2 moles to 1 mole. So 0.52 is the amount that is reacting. So the remaining part is 0.105 moles and 1.04. Did you understand that? Okay, right. So what is the total number of moles now remaining? What happened? Right. What is the total number of moles remaining? Total number of moles. Can you tell me 1.04 plus 0.105? This is the total number of moles that is present. Is it clear? 1.04 plus 0.105 is equal to 1.145 is the total number of moles. After the reaction, number of moles have changed to this number. Is it clear? So what is the pressure? Pressure is equal, PV is equal to nRT divided by V. What is the number of moles? 1.145 moles or 8.314 joules per moles per Kelvin. What is the temperature? Temperature is still 27, didn't change, 300 Kelvin. And what is the volume? What is the volume? Volume is 2 10 to the power minus 3 cubic meters. So now the new pressure would be, check whether you understand that, 1.145 multiplied by 8.314 multiplied by 300 divide by 2, 10 to the power minus 3 is equal to 1.428. 1.428. 10 to the power 1, 2, 3, 4, 5, 6 kilo. Is it right? Ah, right. Let me double check that. 10 to the power minus 3. Then this one also 10 to the power minus 3 it should be. So 10 to the power 6. Can't have a big difference like that. So what is the change in the pressure? Change in the pressure is subtract. Earlier it was 2.076. 2.076. Now it is 1.428. 10 to the power 6. What is the answer? 2.076. 2.076 minus 1.428 is equal to 0.648. 0.648 10 to the power 6 pascals. That means 6.48 10 to the power 5 pascals. Is that clear? Minus 2. Okay, minus 2. If it is minus 2, 10 to the power minus 2 cubic meters. Yeah. Okay. So if it is that, we will change this one, right? 10 to the power minus 2. Yeah, sorry. That means this is 10 to the power minus 5. 10 to the power plus 5, right? And this one is also 10 to the power minus 2. That is where the mistake is, right? 10 to the power minus 2. And this will give you 10 to the power 5. And this is also 10 to the power 5. This is 10 to the power 5 as well. So this will become 10 to the power 4. Yeah. Is it clear? Did you get that answer? Anybody who has done this? Yeah, okay. Right. Yeah, 10 to the power minus 2. Anybody who has done the calculation? Did you get the same answer or different answers? Okay, right. So one of you confirmed, right? Others also same as, right. Okay, right. Okay, fine. 6.48 10 to the power 4 is your answer, right? What I have written is wrong. Let me double check it as well so that next year at least we will have a correct answer. 6.48 10 to the power 4. Right. Thank you. Is it clear? Question number 52. Did you try the next one? Did you try the next one? Next one is question number part B. Part B is the next one. Did you try that? Part B. Part B, write a balance equation for the reaction between Ki and sulfuric, which produces K2SO4, iodine, hydrogen sulfide, and water. So I minus H2SO4 is your compound, right? These are the two things that are reacting with each other. And it says it produces iodine and it also produces hydrogen sulfide, H2S. Let's look at the oxidation numbers. Here it is -1, here it is 0. So the change in the oxidation number is 2 electrons. Here it is +6. This is -2. Here the change in the oxidation number is 8 electrons. 8 electrons. So you multiply this by 4. Is that clear? 4. So if it is 4, this should be 4 times, this is iodine, 8. Sulfur, that is, I think it is balanced. Now let us balance oxygen. How do you balance oxygen? By adding water. How many water molecules? How many water molecules? You need to add 4 water molecules. Right. So 4 times 2, 8. 2, 10, already 2 hydrogens, so need to add the 8H plus. Now I think everything is balanced, right? So now we can write the entire reaction here. Here you have 8H plus. That means you need 4 sulfuric. With this sulfuric, I think you get 5 sulfuric. So 5 sulfuric, H2SO4. Here you need 4 of them. Here there's 1, altogether 5 sulfuric. And here you get 8 Ki. And when you look at the reaction, you get 4 iodine. You don't have to counterbalance this. H2S, you get 4 water. And what else? You get, there's 8K potassium. So you get K2SO4. How many K2SO4s do you need? You have 8. That means 4. 4 times 2, 8. So 4 sulfur with that sulfur, 5 sulfur. That will be okay. I think that is the balance equation. But I hope all of you got the idea, right? Some of you have written the answer also, right? So I think everybody has got it. One of you asked me, like, how do you get 5 sulfuric? Right? Who asked that? Okay, right. It's gone. 5 sulfuric, you get it from this. Here you have 1 sulfuric. 8H plus means you have to have 4 sulfuric. 4 times 2, 8. And this sulfuric and this sulfuric add together, you get 5 sulfuric. That's how you get that, right? Okay. Then it says calculate the volume of hydrogen sulfide during the reaction between the excess of H2SO4 and 16.8 grams of Ki at the standard pressure, room temperature and pressure, right? Okay, can we write only the upper part of the exam too? It can very way, because it says all the reactions, all the products are given, right? It says K2SO4 is formed, iodine is formed, H2S is formed, water is formed. Then they might deduct some marks if you put that, right? Okay, right. So, like, you can't, like, you have to write the entire reaction like, the way that they have posed the question. Right. Okay. So let's look at the next one. Calculate the volume of hydrogen sulfide during the reaction between excess 16.8 Ki. So what is the number of moles of Ki? Number of moles of Ki is equal to the mass divided by molecular mass. What is the mass? 16.8 grams. What is the molecular mass? Potassium is 39. Iodine is 127. We altogether 166 grams per moles. So what would you get? 16.8 divided by 166. That will give you 0.101, right? 0.101 moles. So let us look at the volume. Volume is equal to nRT divided by pressure. What is the number of moles? 1.101 moles. R is equal to 8.314. 8.314 is joules per moles per Kelvin. Temperature is, what is that? It says standard temperature and pressure. Standard temperature for gases is 273, 0. And pressure is 180 m, 1 point, let us say 110 to the power 5 pascals. So what is that answer? 0.101 multiplied by 8.314 multiplied by 273 divided by 110 to the power 5 is equal to 2.29 10 to the power minus 3. Is that what you get? 2.29 10 to the power minus 3 cubic meters. Right? So if you want to convert it to milliliters, you have to multiply by 10 to the power 6. So volume in milliliters is equal to 2.29 10 to the power minus 3 multiplied by 10 to the power 6 milliliters. What is that? 200 29 milliliters. Is that what you get? Yeah, right. Yeah. So that is hydrogen sulfide volume. Ki, ned. Yeah, yeah. Hydrogen sulfide volume, not the Ki volume. Yeah, yeah. So hydrogen sulfide means if it is this, you need to divide it by 8. This one multiplied by 8. 1 over 8. 229 divided by 8 is the answer. 28.6. Yeah. Is it clear? 28.6 is the answer. Right. 28.6 milliliters. What is the answer? 286. There's something wrong. No? These answers are not that correct. 28.6 is okay. Everybody understood that. Right. I'll double check again. Nah? I'll double check. Right. 2.29 10 to the power minus 3 times 3 10 to the power 6. Yeah. 2290 and divide by 8. 2290 divide by 8. Okay. So this is 286. Then it's okay. Right? Yeah. I made a mistake. This is wrong. So this one is 2290. And divide by 8 for get the hydrogen sulfide. Oh yeah, 273 can makati puta. 273 is 273. That's okay. Yeah. What about multiplying the volume? Okay, yeah, you can do that. Yeah, that is also okay. Right? You can look at the number of moles, Ki to hydrogen sulfide, and then look at this 22.414. I think you get the similar answer. We can double check also, right? The potassium iodide is 1.101. The number of moles of Ki is 0.101. So what is the number of moles of hydrogen sulfide? Hydrogen sulfide is 1 over 8, 0.101 moles. So what is the volume? Volume of hydrogen sulfide is equal to 1 over 8 times 0.101 multiplied by 22.414 liters. So that way also you can calculate, I think. 0.101 multiplied by 22.414 and this divided by 8. That gives you 0.283. 0.283 liters. So if you convert it to milliliters, 283 milliliters. Why there is a slight difference? This is because we take it as 1 here. The actual pressure is 1.013. So 22.4 comes with 1.013. Is it clear? Yeah. Is it wrong to use? No, it's not wrong to use. That is right. 22.414 is the one that we use to calculate R. So it's the same equation. There's no difference in it. There's nothing wrong in it. Is it clear? Right. So how about question number 53? Were you able to do it or do you want me to discuss that? Question number 53. 53. Yeah. So let us look at derive the Dalton's law of partial pressure using PV NRT. Let me remind you this one, right? When you have NA and NB here, right? The partial pressures are PA and PB, right? And altogether total pressure becomes PT. If you remove A, you get only B. There you have NB number of molecules. Partial pressure is B. If you remove B, you get a gaseous chamber, and there you have only A, you contain only Na, and the partial pressure is Pa. PV is equal to nRT. PBV is equal to NBRT. And if you look at this one, PAV is equal to NART. Right? And if you look at the total pressure, PTV is equal to Na plus NBRT. Right. So what is Na? Let us say equation 1 here. This is the equation 2 and this is the equation 3. If you take the first equation and divide by the second equation, you get PB divided by PT is equal to NB divided by Na plus NB. PB divided by PT is equal to molar fraction of B. So then you can say PB is equal to molar fraction of B times PT. That's all. So likewise, I think we can work out how the partial pressure and the molar fraction vary, right? Okay. Then let us look at the part B here. A gaseous mixture contains nitrogen 75% based on the volume and oxygen the remaining 25% based on the molecule. The volume this volume has a pressure of 110 to the power 5 pascals. Temperature 300 Kelvin. Assume the ideal gas behavior and calculate the partial pressure of oxygen, right? So if you know the pressure, you know the volume fractions, you can calculate the molar fractions, right? So you know volume fraction is equal to molar fraction. Is equal to molar fraction. So what can you say? You can say molar fraction of nitrogen is equal to 75 divided by 100. 0.75. Volume fraction, molar fraction of oxygen is equal to 25 divided by 100. 0.25. Is it clear? So volume fraction is equal to molar fraction. Now, if you know that, we can calculate the partial pressures. Partial pressure of nitrogen is equal to molar fraction of nitrogen times total pressures, PT. Molar fraction of nitrogen is 0.75. What is the total pressure? Total pressure is 110 to the power 5 pascals. That means 7.5 10 to the power 4 pascals. Right? And then the next one is partial pressure of oxygen is equal to 2.5 10 to the power 4 pascals. Is it clear? Everybody understood that? Did you all understand that? Partial pressure of oxygen in the mixture. So you know the partial pressure of nitrogen, you know the partial pressure of oxygen. You can straight away calculate the partial pressure of oxygen because molar fraction is 0.25. And then they say density of the gaseous mixture. Now, you know PV is equal to nRT. N is equal to simple M divided by capital M RT. Density is equal to P capital M divided by RT. P capital M divided by RT. Right. Now what we need is we need to get the molecular mass. What molecular mass? Average molecular mass. How do you calculate the average molecular mass? So M average. Molecular mass average, nitrogen 75%, oxygen 25%. Nitrogen is 14, 14, 28. So 28, 75%. Plus oxygen 25%. Oxygen is 32, 25%. So this is the average molecular mass. Just like when you do isotopes, just like that. So what is that? 25 times 75 plus the other one is 32 times 25 and then divide by 100 is equal to 29 grams per moles. Now what do they ask? They ask you to calculate the density. Density is pressure. Pressure they have given as 110 to the power 5 pascals. Molecular mass is 29, 10 to the power 3 kilograms per moles. Divide by RT, 8.314 joules per moles per Kelvin. Temperature is 300 Kelvin temperature, 300 Kelvin. So Pascal means Newton meters, like, cubic meters. Kilogram per cubic meter is your answer. This and this also cancels out. 10 to the power 3, 10 to the power 5, 10 to the power 2 cancels out. 29 divided by 8.314 times 2. 1.744 kilo then. Is that what you get? Density of the gaseous mixture. Over 29 divided by 8.314 multiplied by 3. Yeah, 1.162. If you divide that. 1.163. 1626 kilo. Right? Is it clear? Yeah. Why did you take the average molecular mass? Because it is not fully nitrogen. It is not fully oxygen. It's a mixture. So you look at the average molecular mass when you have a mixture in order to get the density. It's not pure oxygen or pure nitrogen. So you need to get the average molecular mass when you say molecular mass. Is it clear? Average molecular mass means total mass divided by total number of moles. Total mass is, if you take total number of moles as 100, 28 times 75 is the total mass of nitrogen. This 20, 32 times 25 is the total mass of oxygen. Divided by 100 is the total number of moles. That is called the average molecular mass. Like when you have two isotopes, I think we discussed this kind of calculation earlier also. When you have two isotopes, we take the average atomic mass, just like that. These are different molecules. You take the average molecular mass in that mixture. Okay? You are provided with a real gas. You are provided with a real gas. You do not know the molecular mass of this gas. How do you demonstrate that it has non-ideal gas behavior? So what you do is you take a sample of this, keep the temperature constant, change the pressure and measure the volume. Change the pressure, measure the volume. Change the pressure, measure the volume. So likewise, you do that. And what you do is you now plot PV product. PV product versus the pressure. And if you get a plot like this, it is an ideal gas. And if you get a plot like this or this, that is a non-ideal gas. Even this kind of a thing is a non-ideal gas. So this one or this one or this one, that gives you non-ideal gas. This gives you the ideal gas. Everybody understood that? How do you demonstrate the non-ideal gas behavior? For 51, 52, 53, I think we have now done. And this briefly explain the experimental procedure to determine the volume of 1 mole of oxygen in your lab. Yeah, we discussed that. This is straight away from the theory. It is in the note there, right? How do you determine the molar volume of oxygen, right? ඒක පොඩ්ඩක් බලන්න, right? Okay. The question number 54. How does it work? Did you do it? Got the answer? 56 I can explain, but 54, 55, if it is okay, I can go to 56. Anyone want me to discuss question number 55, 56? Need 54, 54, 54, 55? 54. Okay. Right. Question number 54. Let us look at question number 54. A and B are connected to each other. I'm going to do only the question. At the beginning, the tap where the connected bulbs are closed. Bulb A contains nitrogen, bulb B contains ethene. Two gas bulbs are kept under conditions given below. So you have a container here and you have another container there. And these two containers are connected together. Like this. Just like that. Right? And the conditions are given. The tap was opened and the two gases were allowed to mix independently and completely. However, the temperatures of each bulb is kept constant at their initial values. Assume that both nitrogen C2H4 behaves ideally and that the volume of the tap is negligible. Calculate the following units. So this one is nitrogen here. In this nitrogen, you have 10 cubic meters, 10 to the power 5 Pascal pressure, and 400 Kelvin. On the other side, you have CH2, double bond CH2, ethene. 5 cubic meters, 210 to the power 5 Pascal pressure, and this is 300 Kelvin. Okay, right. So, but the pressures are kept constant. Pressures are kept constant, right? Okay. Number of C2H4 initially present. C2H4. So let us apply PVNRT to the right hand side. Number of moles is equal pressure volume divided by RT. What is the pressure? 210 to the power 5 Pascal pressure. What is the volume? 5 cubic meters. This is Pascal. Cubic meters. What is R? 8.314 joules per moles per Kelvin. What is the temperature? 300 Kelvin. So what is the number of moles? What is the number of moles that you get? You get 210 to the power 5 times 5 divided by 8.314 times 300 is equal to 400.93. So we'll say 400.9 moles. So this is how you get the number of moles of the first part, right? Now, nitrogen initial present in bulb A. So we apply PVNRT to the other side also. N is equal PV divided by RT. Pressure volume. pressure is equal to, what is the pressure? On the other side, 110 to the power 5 pascals. Volume is 10 cubic meters. R is equal to 8.314 joules per moles per Kelvin. 400 degrees Kelvin. 400 Kelvin, nah? Right, okay. So what is that? 110 to the power 5 times 10. Divide by 8.314 times 400 is equal to 300.69. Let's say 300.7. 7 moles. Total amount of the gas that is present. Total is equal to 400.9 plus 300.7. Here then 400.9 plus 300.7 is equal to 701.6. That's all okay. Those numbers are okay. 701.6 moles. Right. Then final pressure of the gas mixture in bulk B. Now when you open this up, right, let me take this, copy it down. Okay, so we will paste it. This is what you have. So what would happen is when you open this up, right, open this up, this will give you this kind of arrangement, right? 10 cubic meter is there. But the pressure, they become equal. Now, you can't have two containers having two different pressures. Meaning, like, the same container, two bulbs having two different pressures. Once they are connected, the pressure is going to change. Pressure becomes the same. So, I'm going to erase that. 10 to the power 5 pascals. Erase this part also. These contain the same pressure. Pressure 1 here, pressure 1 here. Temperatures remains the same. So what would happen? Like, this contains a higher pressure. So some of the molecules move from this side to the other side. Right. Okay. So let me show you this. What is this? This is the number of moles of C2H2. C double bond CH2, CH2. So you have 100.9. So here 100.9, some number of moles went into the other container. From the ethene gas container, some of those gas molecules move to the other container. So here you had the 300.7. 300.7, and that will be X plus X. Did you understand that? Some of the gas molecules move from the ethene sample to the nitrogen sample. Why do I say that it is going from the ethene sample to the nitrogen sample? Because now ethene has a higher pressure and the other container has a lower pressure. So molecules move from high pressure to low pressure so that the pressure becomes equal. Did you understand that? If you do it in the other way around, it will give you a minus answer. So it will automatically correct itself. Right? Right. So now molecules move from one container to another container and the pressures are the same. So let us apply PVNRT to this side. So let us say first one, this is the second one. PVNRT to the first one. Pressure is P1. Volume is 10 cubic meters. Number of moles is 300.7 plus X times R. On that side, 400 Kelvin. This is equation 1. So this is this side, the 400 Kelvin on the left-hand side. right? And the other container, what do you have? P2 times 5 cubic meters. What is the number of moles? 400.9 minus X multiplied by R multiplied by 300 Kelvin. What do you say? Can you explain this part again? You think, I don't know what else to explain, right? There's one container having a high pressure and the other container having a low pressure. You open this up. Right? These are gases. No? Gas molecules move from high pressure to low pressure so that the pressure becomes the same. It's all right. These are rigid containers. The volumes doesn't change, but the gas molecules move and the entire container has a single pressure. Did you understand that? So how do you solve this? Now, let us say this is also pressure one. Nah? This is also pressure one. Everywhere you have the same pressure. Right. Okay. So now let us look at the best way to solve this. Let's divide. 1 divided by 2. P1 cancels out. 10 divided by 5 is equal to 2. This will be 300.7 plus X. And the other one is 400.9 minus X. Multiplied by 4 divided by 3. Is it clear? 2 and this is 2. Right, okay. So now simplify. 3 times 400.9 minus X is equal to 2 times 300.7 plus 6. You have to solve for X. Otherwise, you can't do the calculation. So what is that? 3 times 400.9 minus 2 times 300.7 is equal to 3 to 5x. 5x. So what is the answer? 3 times 400.9 minus 2 times 300 and whatever that number divided by 5 is equal to 120.26. X is equal to 120.26 moles. So this number of moles move. Is it clear, children? Did you understand that part? Up to that part, we will calculate the pressure. But did you all understand that? Are you sure? Right, okay. So if you know the value of X, we can calculate the pressure. So you can substitute wherever you like. So let us say P1. I'm substituting into equation 1. P1 times 10 cubic meters is equal to 300.7 plus 120.26. R is equal to 8.314. Temperature is 400 Kelvin. And here you calculate this using Pascals, right? So and this cancels out. So what is the pressure? Let's calculate that. 300.7 plus 120.26 multiplied by 8.314 multiplied by 4. 1.399 kilon, 1.4, 10 to the power 1, 2, 3, 4, 5. 10 to the power 5 Pascal pressure. Everybody okay with that? Yeah, okay, right, good. You also got that answer right, very good. And then the next thing is this. Final partial pressure of C2H4 gas in the bulb bay. Now what will happen is this. Now, at the very beginning, the gas molecules move from this container to the other container. Now, what will happen is it is going to eventually mix everywhere, right? Everywhere it is going to mix. Whenever it's mixing, what will happen is you get the partial pressure of this C2H4. Partial pressure of C2H4 is equal to molar fraction of C2H4 times the total pressure. What is the molar fraction of C2H4? Molar fraction of C2H4 is this one, C2H4, 400.9. 400.9 divided by total number of moles. What is the total number of moles? Total number of moles is 701.6. 701.6. Total pressure. What is the total pressure? I think 1.4 10 to the power 5 pascals. That's all. Now we can say 400.9 divided by 701.6 multiplied by 1.4 10 to the power 5 Pascal pressure. 7.999 10 to the power 1, 2, 3. 7.9 means 8. 10 to the power 1, 2, 3, 4. 8 10 to the power 5, 4 Pascal pressure. Yeah. Is it clear? That is question number 54. Everybody got that? Okay. Yeah. 400 moles of C2H4 will not be there in bulb A. No. It's not 400. No, like it's everywhere. Like initially it moves, and then the partial pressure is inside the entire container, right? Entire container. It's like even though it says bulb A is the mixture of everything. Like at the very beginning only the gases go from there. After that, every molecule mix everywhere, right? It's a homogeneous mixture finally. It doesn't contain into one, C2H4 goes onto this and it doesn't stay in that corner. It is going to distribute throughout the entire container. These are gas molecules. You understand what my point is? Yeah. So, molar fraction of the entire component, entire container. What is the molar fraction of the entire container is what we need to look at. I hope you got the idea there. Right. Go to the question number 55. Question number 55. Can you do 55 too? Yes, sir. We'll do that. Of course. Question number 55. Balan. Yeah, okay. Question number 55. Let's look at this one. 1.2 grams of a mixture that contains sodium bicarbonate, sodium carbonate requires 3, 6, 10 to the power molar HCl to complete that. Write the balance equation for the reaction between this one. So what is that? Sodium bicarbonate plus HCl. What is the reaction? You get sodium chloride and H2O plus CO2. So this 2, this is also 2. You got the value? Is it clear? Right. Sodium carbonate reaction Na2CO3 plus HCl, not over 2, not, you don't need to here, I think. You don't need to. Sodium 1, sodium, right, HCl, and it gives you sodium chloride and H2O plus CO2. So here it is 2, here it is 2. 2 sodium chloride, right. I hope you got that. Right. 1.2 grams of a mixture contains this. HCl to react completely. So this entire mass is 1.2 grams. First one is what they ask is total number of HCl moles required for the reaction. Number of moles of HCl. What is the number of moles of HCl required? 6 molar, 3, 10 to the power minus 3. Right? 6 molar, you have 3 cubic centimeters. So 18, that means 1.8, 10 to the power minus 2 moles. So this is the number of moles of HCl that is needed. I hope you got the thing. Right? Okay. Clear? Right. Calculate the masses of sodium carbonate and sodium bicarbonate in the sample. So what you do is, this is X grams. So this means what is the mass of sodium bicarbonate? Sodium carbonate. Sodium carbonate is 1.2 minus X grams. Right. Okay. So what is the number of moles of sodium bicarbonate? Number of moles of sodium bicarbonate is equal to X divided by molecular mass. What is the molecular mass? Sodium bicarbonate is 84. Right? So number of moles of HCl is also, for that is X divided by 84 because it is 1:1 ratio, 1:1 ratio. Sodium carbonate mass is equal to 1.2 minus X, and they have given the molecular mass as 106. Number of moles of HCl that is needed is 2 times 1.2 minus X divided by 106. Right? Because it is 1:2. Right? Now, total number of moles is X divided by 84 plus 2 times 1.2 minus X divided by 106. That is equal to 1.8, 10 to the power minus 2. So I think now you can calculate X. How do you calculate that? Cross multiply. 106X plus 84 times 2, 1.2 minus X. What I did was I cross multiply this, and whatever the common denominator, I'm going to take it over there, is equal to 1.8, 10 to the power minus 2 multiplied by 84 multiplied by 106. I hope you are listening to this. Neither. So what is that? 106x. 168 times 1.2 minus 168x is equal to 1.8 10 to the power 1.8 10 to the power minus 2 multiplied by 84 multiplied by 106. I'm just simplifying the corner there. 160.27. Okay, so let's solve this. What I'm going to do is I'm going to take this part here and I'm going to take this part here, right? And then simplify. 168 times 1.2 minus 160.27, 41.33 is equal to 168 minus 106 is equal to 62x. So x, you will get it as, I hope it is right, 41.33 divided by 62. Then 0.66 वगैरह का. This one. 106, I double check that 106, 168. So it's 62. That's okay. I will take this 1.8 10 to the power minus 2 multiplied by 84 multiplied by 106. 160.27. And this one 168 multiplied by 1.2. 41.33, right? Divided by 62. That is what you get, the 0.66 kilometer. Right? I don't know, but we'll double check, but then I think this is what I got there. Right? So masses of sodium carbonate and sodium bicarbonate. So sodium bicarbonate is X. The mass of sodium bicarbonate, you get Na, that's okay. NaHCO3 is right. 0.66 grams. Mass of sodium carbonate is equal to 1.2 minus 0.66. Yeah, 1.2 minus 0.66 is equal to 0.54. Yeah, 53 and 0.57. Right. That's okay, right? Right. Total number of moles of carbon dioxide eliminated. What is the number of moles of carbon dioxide eliminated? Then question number 4. Number of moles of CO2 from sodium bicarbonate. Right? From this one. Number of moles is X. Now this is 1:1. X divided by sodium bicarbonate molecular mass. What is the molecular mass of sodium bicarbonate? 84. Right? Sodium bicarbonate is 0.66 divided by 84 moles. This is the number of moles from sodium bicarbonate only. NaHCO3. 0.66 divided by 84 is equal to 7.85 10 to the power minus 3 moles. Sodium carbonate, number of moles of carbon dioxide from sodium carbonate, Na2CO3. Here then 0.53 divided by 106, I think. 0.53 divided by 106 is 510 to the power minus 3. 510 to the power minus 3 means how many carbon dioxide would you get? 1:1. So that is also that same thing. So the total number, total carbon dioxide is 7.85 plus 5 is equal to 12.85. 12.85. 12.85 10 to the power minus 3 moles. 1.285. 10 to the power minus 2 moles. That's the number of moles. Then it says volume of carbon dioxide eliminated at this pressure and temperature. So volume is equal to PV is equal to nRT divided by pressure. Number of moles is 1.285 10 to the power minus 2 moles. R is equal to 8.314 joules per moles per Kelvin. Temperature is 298 Kelvin. Pressure, what is the pressure? 1.013 10 to the power 5 pascals. What is that? So 1.285 10 to the power minus 2 multiplied by 8.314, 298 divided by 1.013 10 to the power 5. It's equal to 3.14 10 to the power minus 4. 3.14 10 to the power minus 4 cubic meters. So what is it in liters? 10 to the power cubic centimeters, 10 to the power 6. That is 314 milliliters. Yeah, 314. Yeah, 300. It's given as 318 cubic decimeters, 314 milliliters. Everybody got that? Oh, I hope you are there. Yeah. Okay, all of you got the answers right. Okay. So that is 55, 56 also done, right? 54 is done. 55 is also done. Go to the 56. Were you able to do that? 56. Hmm? Couldn't do it. Yeah, we'll discuss that. 56, huh? 56. At 273, 1.05 pascals, the density of this gas is this. Calculate the root mean square speed of hydrogen molecules under these conditions. Right. What is the root mean square speed? C square. Right? dRT over P. So let us substitute this. So root C square root mean square speed is equal to 3RT divided by simple dRT over P. Over P is this. So this will cancel out, right? So you get root 3P over D. Let us substitute it. Root mean square speed. Is it root mean square? Okay, 3. Pressure. What is the pressure? 1.01 10 to the power 5 Newton. Cubic decimeters. Let us convert this into cubic decimeters as well. Cubic meters as well. Cubic meters means you have to multiply by, I think, 10 to the power 3, isn't it? Per cubic meter. But did you understand that? This is grams, no? Grams to kilograms, 10 to the power minus 3. Cubic decimeters to cubic meters per cubic meters, 10 to the power plus 3. I think it is right. Ten to the power minus 2, I think. Right? And then you take the square root of this. 1838.9. 1838.9 Newton meters. Newton meters means joules. Na? Joules means kg m squared s2 minus. Kg and kg cancels out. And you get meters per second. Is it clear? Anything that you didn't understand there? You understood everything in that category, right? Okay, right. Let's finish the next one also then on the other part as well. Right. Look at this one. Calculate the root mean square speed of argon at standard temperature and pressure. Were you able to calculate that? Root mean square speed is equal to, what is that? 3 RT over M. Right? Were you able to calculate that? Right? 3 RT over M, 3 times 8.314, right? Joules per moles per Kelvin. What is the temperature? What is the temperature? Standard temperature, 273, isn't it? 273 Kelvin. What is the molecular mass of argon? Argon is 40. 40, 10 to the power minus 3 kilograms per moles. Kelvin per Kelvin cancels out. Per moles cancels out. And this gives you meters per second. 3 times 8.314 multiplied by 273 divided by 40, 10 to the power minus 3. And then the square root of this. 412, yeah, 412.58. 412.58 meters per second. Udala, you got the idea? Everybody understood that? कोई एक hydrogen can, which one is that? Hydrogen, this one, like, you have given the other data and you have to use that other data and do the calculation. And this is like, right, using 3p divided by d. Do the calculation based on the data that is given, right? Okay. Next one is calculate the kinetic energy of 1 mole of any ideal gas under 1000 Kelvin. What is that? EK, kinetic energy, is equal to 3 divided by 2 RT for 1 mole, right? Is that clear? RT. 3 divided by 2, 8.314 joules per moles per Kelvin. And what is the temperature? Temperature is 1000 Kelvin. So this and this cancels out. And you get, what is the answer? 3 times 8.314 times 1000 divided by 2 is equal to 12,471. 12,471 joules per moles. So that means 12.471 kilojoules per moles. Is it clear? Right. Calculate the ratio between the root mean square speed of oxygen and xenon and 27 degrees Celsius. C squared bar root oxygen to xenon. What is that? 3 RT over M. 3 RT over molecular mass 1 divided by 3 RT over molecular mass 2. So 3 RT cancels out, root M2 divided by M1. What is the molecular mass of xenon? Xenon is 131. Oxygen is 32. And then you take the square root of this. 131 divided by 32 and take the square root of this. What is that? 2.02 Kelvin. 2.023. That is the ratio. Right? Okay. So I think you should do it. The answers are given. I think I discussed, like, more than 75% of the tutorial. Right? I can give you one more day, right? That is next week. Like, just to finish everything, one thing, like, maybe next week I will take this as the very last thing. That's the only thing I can do. Right? Okay. Is it clear? එතකොට we will discuss one or two questions, maybe at least one question from chemical calculation. I think question number 17 in chemical calculation. Tutorial 7, right? Right, this tutorial number 7. And the question number 17. Read the question. Do you have the tutorial with you? Tutorial number, right? Tutorial number 7. Right. 25 cubic centimeters of iodine solution was titrated with 0.1 molar sodium thiosulfate solution. And the iodine reacted with 17.6 thiosulfate solution. Give the reaction equation. So iodine plus sodium thiosulfate. This is a very common reaction. That's why I wrote 2 there, right? Na2S4O6. And then it gives you sodium iodide, Na. What is the indicator used? Describe the endpoint of the titration. Indicator used is starch. How do you describe the endpoint of the titration? You reduce the concentration until it becomes straw yellow color. A yellow color. Add starch and it becomes blue-black. And you continue the titration until it becomes colorless. That's all. Calculate the concentration of iodine solution in moles per cubic decimeter and grams per cubic decimeter. Concentration of the iodine solution, right? So number of moles of iodine to the number of moles of sodium thiosulfate, Na2S2O3, is equal to iodine is 1, sodium thiosulfate is 2. Look, I will. So, what is the thing, right? Let us say iodine is concentration of iodine. What is the volume? Volume is 25 milliliters. Sodium thiosulfate concentration is 0.1 moles per cubic decimeter. And then it is 17.6 milliliters. Is equal to 1 to 2. So what is the concentration? Concentration is equal to 0.1 times 17.6 divide by 25 times 2. And you get a concentration of 0.0532. 0.05325, not 532, 325 moles per cubic decimeter. Moles per cubic, and what is the concentration in grams per cubic decimeter? So we turn this into grams, 0.0352 moles multiplied by molecular mass, sodium 46, sulfur 32, 64, oxygen 48 is equal to 158. 158 grams per cubic decimeter. What is that answer? 0.0352 times 158. Then 5.56. Sodium thiosulfate 17.6. Then 0.1. Yeah. This is what I got. Like, let us double check. Grams per cubic decimeter. Let me double check. 0.1 times 17.6 divided by 2 times 25. 0.0352. That is multiplied by sodium. Sodium 40 is 6. Sulfur, sulfur 64. And oxygen 48. What are your answers? What do they ask? Calculate the concentration. Iodine. Iodine. Not rhodium thiosulfate. Yes. Oh, I'm so stupid. 127 times 2. 254. 254 grams, right? 254 multiplied by 0.0352 is equal to 8.94. The answer is okay. 8.94. It says iodine, not the sodium thiosulfate concentration, iodine. Yeah. Okay. So that's okay, right? You want to do the next one also? Yeah, 254. Yes. Right, okay. Bluish black color to colorless. Yeah. Yeah. Bluish black color to colorless. Oh, තමයි blue black කියලා තියෙන්නේ. Right? Okay. Right. Question number 18 as well. If you are not tired, we will take it as the very last question today. Huh? Right. 1.0 grams of an impure sample of potassium dichromate. K2Cr2O7. You have some impurities also. Total weight is 1.01 grams. Was dissolved in dilute sulfuric and made up to 250 milliliters. (250 milliliters) in a calibrated volumetric flask. Out of that, you take 25 milliliters. Pipetted out into a conical flask and excess potassium iodide was added. You add Ki. And the starch indicator was added. The liberated iodine was titrated with 0.1 molar sodium thiosulfate. 0.1 molar sodium thiosulfate. And it turns into colorless thing, turning after 20 milliliters was added. Construct the full balance equation for the reaction between dichromate and iodide ions, right? So dichromate, Cr2O72 minus plus I minus. I minus turns into iodine, dichromate turns into Cr plus 3. Let's balance it. Plus 6 to plus 3, 3 electrons, altogether 6 electrons. This one you have 2 electrons here. Multiply this by 3. Right? So this by 3. So if you multiply this by 3, this is 6. This one is 2. 7H2O, 7 times 2, 14H plus. බලන්න හරිද කියලා? 14 minus 8 is equal to 6. That's okay. So this is the full balance equation. Write the balance redox equation for the reaction between thiosulfate and iodine. I think we wrote that reaction, right? Earlier also. I will write that, this one. And then I'll paste it here. That is that reaction. Okay. On the other side, calculates the moles of sodium thiosulfate used for the titration, hence the number of moles of iodine there. So let us look at the number of moles of thiosulfate. Number of moles of thiosulfate is equal to 0.1 times 20. 0.1 times 20, 10 to the power minus 3. moles. It is equal to 2 10 to the power minus 3. Right. So if you know that number, you can calculate the number of moles of iodine. Number of moles of iodine is actually half the value, 1 10 to the power minus 3 that is produced. Hence, the number of moles of iodine titrated. Calculate the number of moles of dichromate reacted to give that iodine. So if you look at iodine to dichromate is 3 is to 1. 3 is to 1. So what is the number of moles of dichromate? Cr2072 minus dichromate is equal to 1 over 3 10 to the power minus 3 moles. Right? Iodine is 1, so 1 over 3 dichromate. Dichromate reacts there. Calculate the formula mass of potassium dichromate and the mass of it in 25, okay, titrated. So what is the mass? Mass is equal number of moles times the molecular mass. 1 over 3 10 to the power minus 3 multiplied by the molecular mass of potassium dichromate. 39 times 2 plus 52 times 2 plus 16 times 7 is equal to 294. 94 grams. This is the formula mass is 294. So what is that? 294 times 1 10 to the power minus 3 divided by 3 is equal to 0.098. 0.098. That was in 25 milliliters. So calculate the total mass of potassium dichromate in the original sample. That is 10 times the value, right? So total mass is equal to 0.98. Is that clear? 10 times the value. So what is the percentage? Percentage is equal to 0.98. Total mass that you have taken was 1.01 grams multiplied by 100%. Here then, what do you get? 0.98 divided by 1.01 multiplied by 100%. Is 97.029. 97.029%. 90%. I think right? So that is also done. Question number 19 and 20. I will do this when we meet on Saturday, right? But gradually we can improve. What I'm going to do is I will leave this off. Make the gaseous tutorial. We are going to leave it off, and then maybe next week I can do ichara thamai. I will move on to SPD and we will continue this. Right? And then we'll finish that tutorial. And then we'll start with another energetics. Right? Okay, Putala. Good night, children. Right? Keep on working hard. Don't wait till the last moment. Like every week, you do something that, makes you closer to the thing. Am I? Right? Then it is okay. Right? Okay, right. Okay, good night.